Okay, any other? Okay, so today we start the concept of the control volume. Okay, so let's start from it. So the concept of control volume is if we want to apply the energy balance equation, such kind of, in other words, energy conservation law, then system have to be closed. System closed means the matter or material or some substance does not exchange. Okay, do not exchange. So like let's say in bottle, let's say there is 1 liter water is there, then it will not go outside or other substance does not come in. Okay, it is closed. Energy balance can be applied actually on only closed system. Okay, on only the closed system. However, in real system, let's say like a certain kind of, let's think about a certain kind of cycle or vehicle. Let's think about the vehicle. It looks like a little bit silly. Please, my apologize about my bad hand drawing. Assuming you think about the like, let's say, okay, train, okay, train. Then air have to be comes in. There's combustion takes place, and there have to be exhaust, right? The air comes in and combustion takes place, then there will be exhaust. So actually, it is not closed system because air exchange, right? Gas exchange. So it is not closed system. However, if we would like to apply the energy balance relation, then it is a little bit tricky, right? Because it is like a open system. In other words, gas can be exchanged and other matter also can be exchanged. However, if we would like to apply the energy balance equation, then the concept of the control volume is if we like set certain kind of region, in other words, volume, then we assume that it is we can apply the energy balance equation on it. Okay, he assumes some volume that we can apply the energy balance equation on it. 자, 이거 중요한 개념이니까 한국말로 한번 하겠습니다. 원래 닫힌 개여야만 에너지 밸런스 이퀘이션, 에너지 보존 법칙을 쓸 수 있는데 자동차나 모든 대부분의 엔지니어링 컴포넌트들은 사실 닫힌 개가 아니잖아요. 기체도 왔다 갔다, 자동차도 흡기, 공기를 빨아들이고 안에서 연소를 하고 나머지를 배출해야 되잖아. 이 과정이 있는데 사람들 에너지 밸런스 이퀘이션을 쓰고 싶은 거예요. 그래서 자동차의 어떤 가상의 자동차가 딱 자동차인지는 모르겠지만 어떤 가상의 볼륨을 설정을 하고 이 영역 안에서 우리가 에너지 밸런스 이퀘이션을 만족한다고 보는 겁니다. 좀 난해하죠. It's a little bit tricky. However, actually, if we can, most of the cases, we can find the reasonable control volume. Okay, we can find the reasonable control volume. Then, what is the best choice of the control volume? You can ask. Then, the best control volume is, first of all, it is easy to analyze. Another thing is that by that analysis, if we can get useful information, then it is good control volume. Okay, good control volume. Let's say if like we say like those kind of control volume here. However, for the case if we analyze the control volume analysis on it, but there is nothing useful information on it, then that analysis is like useless. 컨트롤 볼륨을 어떻게 잡느냐? useful information을 뽑아낼 수 있어야 돼요. For example, 뭐 이런 게 있을 수 있겠죠. 예를 들어서 하나만한 분석이 많잖아요. 예를 들어서 for example, if we would like to compare the amplitude of two mountains, let's say like Kwanang Mountain and Gwangyo Mountain, everybody knows that, okay, Gwangyo Mountain is higher, okay? In that case, that analysis is not useful because that information is not really useful because we already know it, right? So the important thing is, it is possible to analyze. Another thing is they have to give some kind of useful information, okay? That two things. So what is control volume? So then since it is not fluid mechanics course, so I do not want to say many things about it, okay? Just I would like to say, okay, there is control volume, then that reason we can apply the energy balance equation, okay? Energy balance equation. So it is kind of concept of the engineering, okay? Concept of the engineering. Okay, move on. So let's say if there are two like here, let's think about the virtual like a reservoir. reservoir는 저수지 같은 게 있다고 생각해 봅시다. Virtual reservoir. Then there's inlet and outlet. Then we can have like a certain kind of control volume. That boundary can exactly same as the boundary of the reservoir. However, it cannot be, right? Because those area setting the boundary is a very technical issue. What is the boundary between inlet and reservoir? It is not really, there is a strict border line, right? There is no strict border line. So anyway, we can set like a certain kind of abstract line and which say it is control volume, okay? So that reason, we want to apply the energy conservation. However, typically, people want to also apply the mass conservation, mass balance. Another reason, another terminology we say is mass balance. Mass balance means, okay, the mass of the rate of the mass change of the control volume is like input is amount of input mi dot, amount of outlet me dot. In other words, outlet we also say it is exit, okay, exit. So inlet exit or inlet outlet, both ways okay, both ways okay. So it is typically very intuitive. DTD-MEV is if there can be like a multiple inlet, then summation of inlet flow and then take the minus and summation of outflow, then it has to be change rate of the mass of the control volume. 매우 단순한 거예요. 은행 계좌 같은 거죠. 100원 넣었다가 80원 빼면 얼마 남겠냐? 20원. 뭐 이런 얘기입니다. Okay? So any questions on this? Fine? Okay. Okay. Here is one concept. Okay. So M is a specific volume. Okay. M is a specific is mass rate. Okay. So let's think about V is a specific volume, which is determined by volume mass. Okay. Volume mass. So in that cases, what is the volume? Volume, let's say, assume those kind of cylinder. And in that case, mass is given, volume is given by A multiplied by height H. Okay, A is cross section, A multiplied by H. Okay, assuming the flow only, we assume the unidirectional flow. Okay, like there is a certain fluid flows with only one direction, then once we know the velocity, okay, once we know the velocity, then V dot is given by V dot is given by A V, which is a velocity. It is not volume. It is velocity of fluid, okay, velocity. Because velocity means nothing but dt dh in this case, okay, dt dh, okay. Let's assume height of the fluid region is h, So once we take the dtdh, it is nothing but velocity. Okay, it's nothing but velocity. So v dot, actually, it is v dot is av. Okay, and divided by m dot is still here. Okay, so in summary, its specific volume v dot. Oh, sorry about that. M dot is actually large v dot. Here is a volume and divided by specific volume. Okay. Here is a large volume and is a specific volume, and it is given by AV. Here is a velocity. Okay. So there are two ways. Please don't be confused. So in your textbook, I make the italic because to prohibit the confusion. Okay. To prohibit the confusion. Okay, and inverse of the specific volume is nothing but a density. Okay, it's nothing but a density. So we can write down like this way. Okay, so any questions or comments on this relation?
Professor,
Yes.
아까 그 V dot is
Okay, in English.
volume rate.
Yes.
V dot is V dot. You, Professor, you said that V dot it
is
means
AV.
That means volume rate or what?
Here is it is volume rate. Okay, here's volume rate, and here is now like a velocity. Okay, so that two ways different. So volume the velocity I represented in the bold. Okay, bold symbol. Okay, bold symbol.
Professor, I have a question.
Yes.
How does the P came out?
P, where is P? Here? This?
Yes, yeah, PAV. No.
Rho is a density.
Thank you.
Rho. Okay. Then we would like to move on the other concept that, okay, then what is the steady state? Steady state means the state of current volume does not change with respect to time, okay? The state of the current control volume, state of the control volume does not change with respect to time. So dmcv dt equals 0, okay? It means mass of control volume does not change. Okay, mass of control volume does not change. So in that case, those two values have to be balanced. Okay, it's quite obvious, right? If you earn $100 and you spend $100, then your balance have to be 0, right? So in that, so it's like the same as the balance, right? Balancing. Okay, so here is balancing. Okay, so there used to be a typo here. So in the blue side, it means there used to be typo. So we have the opposite. Okay, we have the opposite. So think about here. Okay, so let's assume those system. Okay, let's assume those system, and control volume is here. Okay, control volume is here, and we assume that there are 2 inlets and 1 outlet. Okay, there are 2 inlets and 1 outlet. So why there is positive sign? Because it is inlet, and outlet, there have to be negative sign. Okay, positive sign, negative sign. So by that way, we have that M2 dot is M3 dot negative M1 dot. Okay, okay, by that way, first of all, we have M1 dot is already written in the problem, right? 35 kilogram per second. Okay, 35 kilogram per second. M2 dot, we don't know. We would like to calculate it. M3 dot, there is no, but however, there is some information on it. Okay, there is some information on it. So we would like to utilize it. Okay. formally, we studied about those relations here. Okay, we studied about those relations. So once we divide the specific volume, then we can calculate the M3 dot. So those specific volume is coming from table 19.2. Okay, 19.2, and we have what kind of information? Pressure. Okay, we have pressure information. Okay, go to 19.2. Okay, go to 19.2. And what was the pressure? Tell me, what was the pressure?
6 bar.
6
R입니다.
bar. Okay, here. So now we have the specific volume here, right? Specific volume here. So we can utilize those information. You can utilize those information, and by that reason, and there used to be a confusion, and it is like I multiply 10 to the 3 in the table means, okay, we multiply the 10 to the 3 to that value. So originally it means it is 1.1006 multiplied by 10 to the negative 3. And 0.05 is in the problem. Okay, so once we divide it, then we can calculate the M3 dot is 45.43, 45.43. So therefore, M2 dot is given by 45.43 negative 35. So we found that, okay, M2 dot is 10.43. Okay, we found that by the mass balance. Okay, by the mass balance. Okay, then how can I calculate the V2? How can I calculate the V2? Also using those relations. Okay, using those relations, we can calculate the V2. And at the, okay, inlet 2, there is information of the cross section. Okay, there is the information of the cross section. So once we divide it, then we can calculate the flow velocity. Okay, flow velocity, and which is given by 5.74 meter per second. So what is the main assumption? Main assumption is it is a steady state, so mass of the control volume have to be conserved. Using that relation, everything is going on. If something is not clear on this problem, please let me know.
I have a
If-
question.
Yes?
In the inlet 2, I mean the state 2, how do we know for sure that it is still saturated liquid?
So who are you?
김용세입니다.
누구요?
김용세입니다.
김효수. It doesn't matter. It doesn't matter. However, yeah, okay. Since we say in this case, there is a huge assumption that all phases are in the liquid. Okay, maybe it can be also still water. However, from the information about the temperature and pressure, it cannot be vapor. Okay, it cannot be vapor because we already know the temperature and pressure. Okay.
Okay.
Yeah. Any other? It's a very nice question. Okay. Every question is very nice. Actually, every question is very nice. Okay. So, control volume. First of all, we can, since it is steady state, okay, so we can apply the mass balance. Okay. Okay, conservation of energy for a control volume. Okay, think about here. So let's assume we just consider about the internal energy. However, system can have kinetic energy or potential energy. Okay, kinetic energy or potential. 그냥 하는 얘기는 임지현 학생 깜짝 놀랐어요. 뭐 무슨 벌레가 있는 줄 알고. 뭐 머리에 뭘 꽂고 있네요. 아니 좋습니다. 무슨 벌레인 줄 알고 피하라고 할 뻔했어요. 깜짝 놀랐습니다. 그래서 벌레가 너무 크대라고 생각을 했는데. 네. 그렇습니다. 오케이. by the first rule, it is Q minus W. Okay, it is Q minus W. And dTdECV, okay, dTdECV is given by Q dot minus W. It means just we take the derivative with respect to T. So it is kind of waveform of the energy conservation, okay, waveform of the energy conservation. So we also put those all derivative on it. It is nothing but just to take the derivative with respect to T. Think about it. Take the derivative with respect to T, then it becomes waveform, okay, waveform. Okay. Assume that there is inlet and outlet, okay, inlet and outlet. Assuming that since then energy change, okay. So first of all, we do not think about those two terms, okay. At this moment, we do not think about those two terms. So the change of the internal energy at like a control volume, okay, control volume is given by internal energy difference between waveform, in waveform, internal energy difference between exit and inlet, okay? Because exit is added one, inlet is added one, and exit is out one, okay? Okay, how about the change of the kinetic energy? Change of the kinetic energy is also given by kinetic energy difference between exit and inlet, okay? What is the rate of the potential energy difference? Is potential energy difference between exit and inlet. Actually, there is some assumption there, okay? Actually, there is some assumption. However, I think it is just, there is some assumption means, okay? There is a huge assumption that here is the control volume and we have the inlet and outlet. If certain property changes here, then it is given by difference between exit and inlet. Okay, that is a huge assumption. Okay, that is a huge assumption. However, generally, it is quite reasonable assumption. Okay, it is quite reasonable assumption. You know what I mean? Okay, if there is a certain property changes, then it is given by the rate difference between exit and inlet. Okay, exit and inlet. That is assumption. Okay, then it is by the control volume analysis we would like to do. Okay, so now we have the energy balance equation. Now it changes like this way, right? Because using the information here, okay, using the information here, that is energy balance equation. Okay, then W dot is delta F dL dt. Force is given by pressure multiplied by area. Force is given by pressure multiplied by area. And delta dt dl, and we say dl dt. dl dt means assuming like those kind of area and one directional flow. So dt dl means velocity. Okay, dt dl means velocity. So it is given by delta PAV. Okay, delta PAV. So in the mechanical work, we can have delta dot is PAW. So total W dot is given by W dot of the control volume, and there is work of the at exit and work out in the inlet. So their difference term, okay, their difference term is there. And we already have the relation that AV is M dot V, AV is M dot V. So finally, we can write down W dot is W dot is given by W dot CV, M dot PV, M dot PI, VI. Okay, where does it come from? Because we have the relation here. So AV can be replaced by M dot V. Okay, AV can be replaced by M dot V. So we replace those AV to the M dot V. So still there is pressure there. So we can write those four. Okay. So far, okay, I will give you 1 minute. Something is not clear, then please ask me. Up to 6.5. I will give you 1 minute.
Professor, I have a question.
Yes.
Why there is W dot CV?
Because control volume, also there is a certain kind of work rate. Okay. Without the inlet and outlet, W volume also there has some kind of work. Okay, very nice question. Any other? Fine. Okay. Okay. Then finally, now we have the QCV. We assume that, okay, Q is is the heat transfer, the boundary of the control volume. So there can be Q dot is assumed by same as Q dot CV. Okay, Q is assumed by Q dot is assumed by Q dot CV because there is assumption that heat cannot be generated inside the control volume. But I would like to ask, if there is a kind of chemical reaction or nuclear reaction, then heat can generate, right? Let's assume there is a certain kind of chemical reactions or nuclear reaction, then heat can generate. But in this case, to simplify the problem, we do not take care about those kind of reactions here. 예를 들어서 컨트롤 볼륨 안에 화학 반응이 있거나 핵 반응이 있으면 hit도 만들어질 수 있죠. Q.CV랑 Q 다시 다를 수 있지만 이 경우에서는 그러한 화학 반응, 핵 반응 이런 건 고려하지 않는 겁니다. 문제를 단순하게 하기 위해서. Okay. Okay. Then Q dot is replaced by Q dot CV. So finally, we can write down rate form of the equation. Energy is given by here. Okay. And we already studied that. We already introduced enthalpy, which is U plus PV. Okay, enthalpy is given by U plus PV. So using the enthalpy, here is enthalpy, here is another enthalpy. So we can write down the waveform as here. In those cases, we assume only one inlet and one outlet. Assuming there are multiple inlet or outlets, then we can replace the sentence. Okay, we can replace the sentence. Okay. Any questions? Up to 6.8.
Professor, I have a question.
Yes.
That U internal energy U and enthalpy H is
Yeah.
specific internal energy and specific enthalpy.
Yes.
So that small letter.
Yes. Right.
Uh,
Specific enthalpy is enthalpy divided by mass. Specific internal energy is and internal energy divided by mass. Okay.
so that we use it now and
Okay. Yeah, actually we multiply by mass to there, then it becomes just enthalpy. However, we want to control those mass rate separately. So actually, if we multiply it, then it becomes same. Okay, it's total enthalpy. It becomes. Okay. Assume there is no accumulation of mass within the control volume. It means mass does not change. Okay, mass does not change. So we can write down this way. Okay, those quantity is same as here, and we can represent it by like m dot. Okay. So we can replace by m dot and m dot, then waveform of the equation can be rewritten by here. It can be rewritten by here. So there are two devices, nozzle and diffuser. Maybe you have learned about this, okay? Or you go to market, there is a nozzle and diffuser. Like recently, people say diffuser is kind of perfume, right? Perfume, like a perfume in your room. People say it is kind of diffuser. That diffuser is different from here. Okay, it's not that diffuser. So there are two devices. Then what is nozzle and diffuser? Actually, it is a little bit tricky. However, in general, we say when we, like, let's say here is in outlet and inlet, then V2 is bigger than V1, then we call it is nozzle. And V2 is smaller than V1, then we say, okay, here the figure it becomes opposite. Okay, sorry about that. No, that is correct. Sorry, that is correct. It is not volume, it is velocity. Sorry about that. Velocity and pressure. It is not volume, velocity. So when V2 is bigger than V1, so it means the fluid is more faster at V2 because the area is small. Okay, the area is small. Then we say it is nozzle. And when V2 is lower than V1, it means P2 is higher than P1. Then we call it is a diffuser. Okay, we call it diffuser. Okay. We can divide by m dot. Okay, we can divide by m dot. Then it can be written by the equations here. Okay. And there is a certain quantity here that we say that is rates of energy transfer per unit mass flowing through the control volume. So it is energy transfer per mass by the heat. It is energy transfer per mass by the work. Okay, that we can say that. Okay, any questions on this? Fine. Okay, let's think about the case of nodules and diffuser. Okay, nodules and diffuser. We would like to make the problem a little bit simple. Okay, we would like to make the problem a little bit simple. So we assume that there is energy transfer by the work does not present. Okay, it is not present. So we assume it is zero for nozzle and diffuser. Okay, for nozzle and diffuser. So only this term is survived. Okay, only this term is survived. Here this term, here is some, here is term. In practical case, since there are not many cases where the height of the inlet and outlet is dealt with greatly, it means amplitude of the inlet and outlet is usually comparable. Okay, usually comparable. The difference in potential energy can be neglected in many cases. If we have to consider, then we have to survive this term. However, if this term is negligible, then we usually omit this term, okay? Assuming that amplitude of inlet and outlet is comparable, okay? Assuming inlet and outlet is comparable. Okay, now only 3 terms are survived, okay? Now only 3 terms are survived. So this is not only, however, universally used the energy waveform for the nozzle and diffuser, okay? We usually apply these types of energy rate equation for nozzle and diffuser. 하나 얘기하고 싶은 것은 궁금증이 들 수 있어요. 노즐 앤 디퓨저에서는 이렇게만 써야 되나요? 저의 대답은 그렇지는 않습니다. 상황을 봐야 돼요. 상황을 봐야 되지만 일반적으로 별다른 얘기가 없으면 이렇게 쓰는 것 같아요. 저도 여기서 더 여러분들에게 추가적으로 얘기하기 어려운 이유가 있는 게요. 저도 노즐이랑 디퓨저에 대한 서머다이나믹 어널리시스를 실무에서 해보지 않았기 때문에 실제는 어떻습니다라고 얘기하기는 어려울 것 같아요. 실제는 어떻습니까? 얘기하기는 어렵지만 텍스트북상으로는 이렇게 많이 씁니다. 텍스트북상으로는. 네, 저는 이 정도 얘기할게요. 네, 저는 뉴질랜드 디퓨저를 실무적으로 다뤄본 적이 없습니다. 그래서 더 이렇게 뭐 앰플리튜드 차이가 있으면 어떡합니까? 저의 지금의 생각은 넣어주면 될 것 같아요. 넣어주면 될 것 같습니다. Okay, so steam enters a nozzle. Okay, so in that case, steam enters a nozzle operating at inlet condition. P1 is 40 bar, T1 is 440 degrees Celsius, velocity 10 meter per second. Steam flows through the nozzle with no heat transfer, no change in potential energy. So there is a problem. I already give two conditions. No heat transfer, no change in potential energy, okay? So please neglect two terms. The mass flow is 3 kilogram per second. At outlet 10 bar, 500 meter per second, okay? 500 meter per second. So you can see here, this is nozzle and the difference between velocity is very high, okay? 10 meter per second and 500 meter per second, okay? So here the pressure is way higher, 40 bar and 10 bar, okay? Here. Let's go to the analysis. Equation 6.12, and they assume that, okay, now we want to omit heat transfer or change in potential energy. So no heat transfer means this term is also zero. Okay, this term is also zero. So at state one, okay, at state one, there is information about the 40 bar and 440 degrees Celsius. Okay, so let's go to the 19.3. So what is the pressure?
40 bar.
40 bar, right? So go to the 40 bar. Okay. Okay. Now we find the 40 bar. 40 bar here. What is the temperature?
440.
440. Okay, very nice. So we can read the enthalpy, right? We
one.
know what 440.
Yes.
Right? So here, okay. So we can read the enthalpy, right? So there is a pressure and temperature. So we can read the enthalpy, okay? That's how we read the steam table, okay? That's how we read the steam table. So go back. Go. And oh, please. So we can read the H1 from the table here. As state 2, okay, and state 2, we do not know the H2 value. However, by the balance equation, we can calculate it. Since we know the H1, so we can calculate the H2 as well, right? So H1 plus this much. We know the H1 and we know the velocity of the two state. So we multiply here, then we can get, okay, it is H2 by the energy balance. Okay, by the energy balance, we can calculate H2. What is the pressure of the, okay, then go to that, 19.3. So what is the pressure at the state 2? Pressure?
10 bar.
10 bar. And what is enthalpy value? What is enthalpy?
3,100.
3,182.
82. Yes.
1,082. So we found that it is placed between two rows, right? It is placed between two rows, right? So we choose those two temperatures, 360 and 400. And by interpolation, we can assume the temperature. Okay, we can assume the temperature. So let's go back. Okay. So now I think you have the clear picture. Why do we choose those two temperatures, 360 and 400? Okay. So here we can read those two values and specific volumes. So by interpolation, we already obtained H2 is here. Here is H1 and difference between, okay, and difference between two values, right? What two values means difference between here and here. Okay, subtract this much from here. Okay, it is 85. Okay, subtract those much, it is 85. And that is interpolation, like let's assume the H changes linearly within the between 360 to the 400. Then by this relation, we can estimate the T2, right? We can estimate the T2, and T2 is given by 361.69 degrees Celsius. So once we have the temperature, then we can also estimate the specific volume at temperature 361.69 degrees Celsius by the same consistent interpolation formula. So we already know the V100, 360 and V400. By those relations, we can estimate the V2, and it is given by 0.2876. Okay. And finally, since we know the specific volume, since we can have the area of the A2, and that is given by this much. So, so there is a problem used to be determine the area of the exit. So that's how we can evaluate the area of the exit. Any questions on the how can we solve this problem, or what is that? So is there any questions?
Question.
Yes.
Why did we use the interpolation twice instead of one?
Because first of all, we have to evaluate the temperature from the, because
Okay.
we do not know the temperature of the exit. So by the interpolation, we have to interpolate the temperature first. And then by another interpolation, we have to estimate the specific volume at the exit, okay, to evaluate the area of the exit, okay?
Can we just interpolate by specific volume
By
from
specific
enthalpy?
volume. Very good question. I think specific volume. So how can we evaluate the how can we? Okay, for the okay the okay at this moment. Okay, okay. Now we have the enthalpy, and we just interpolate. So we do not know the temperature. So how can we interpolate by volume? I don't understand. Interpolate by enthalpy?
What I mean was interpolate between the specific volume by the given enthalpy.
Oh, okay, okay.
So not going through with the temperature, just
okay,
go
so
straight.
you are talking about let's say V equal V third 6. Okay, but if we do not evaluate the temperature, then we can choose 360 and 400. Because at least we have to know those two values to evaluate. However, without that, I think is it not it is possible to evaluate using the enthalpy, or maybe I can okay, maybe I do not catch your question. That is correct. So you do not want to evaluate the specific volume using the value of the 360 or 400? That's what you are talking about?
그, 그 엔탈피 두 개를 알고 있고, 그
예.
이제 표를 보시면
그래서 360,
엔탈피,
400, 그 다음에 V를 어떻게 한다는 거죠?
그러니까 엔탈피랑 스페시픽 볼륨 간의 인터폴레이션을 하면 되지 왜 온도를 거쳐서 인터폴레이션을 두 번 하는지 잘 모르겠습니다.
그럼 이렇게 한다. 뭐 예를 들어서 볼게요. H2 minus H1 아닙니까? Sorry. Maybe we can do like, let's say, I would like to say it's VT, then H2 minus H1, H2 minus H1 multiplied by HT minus H1. That's what you are talking about? Since at temperature T, we say it is specific volume, and we know the HT or HT here. So maybe it can be H2 you are talking about. Maybe I would like to change. So you are talking about, here is H2 minus H1 is correct?
I'll check and tell later.
오케이. 엔탈피로 하는 것도 잠깐만요. 좀 생각을 해볼게요. I think maybe
예,
this way is possible.
문제에 적혀 있는 대로 하면은 굳이 T를 안 거쳐도 되는데
360 H2 minus H1 and H2 minus H1 H400 빼기 H300
뒤에 괄호 부분
이 괄호
볼륨.
부분에 볼륨이 들어
네.
이렇게 V2 minus V1 okay. Then we know the H2 and H1. Okay, we know the V2 minus V1. And okay, let's start from that. That is V2. We would like to have V2, right? We would like to have V2. Okay. 자, 나갈 학생들은 나가세요. V1. V2 is V1 plus. So okay, maybe I can change. $400 and H1. That is true? 그럼 여기 V2 minus V1이 다시 들어가나요?
거기서 이제 좌변이 그냥 구해야 되는 스페시픽 볼륨입니다.
그러니까 구해야 되는 스페시픽 볼륨이 V2잖아.
아닌 거.
네, V2를 구해야 되잖아.
V2고 V1이 아니라 V360도 아닙니까?
V1이 360도가
그러니까 V1 대신에 V360도가 들어가야 될 것 같습니다.
360. 이것도 360. 오케이. 이렇게
네.
하고.
그리고 곱해지는 값도 V2 마이너스 V1이 아니라 네, V400 마이너스 V360이면 될 것 같습니다.
오케이. 무슨 소리인지 알겠어요. 지금 저의 생각으로 안 될 건 없을 것 같은데 값 차이가 크게 나나요?
그 온도로 계산했을 때가 값 차이가 더 부정확한 것 같습니다.
부정확하다는 건 뭐 대비로 부정확하다는 거예요?
이제 인터폴레이션이 이제 선형적으로 증가한다는 가정인데, the difference between the two temperature는 이제 40이고, 이걸 그냥 바로 specific 볼륨으로 계산했을 때는 좀 더 dense 해가지고,
이렇게
네.
계산한 V2 값이 얼마예요? 이렇게 계산해 보면
똑같이 나오는 걸로 알고 있습니다.
똑같이 나와. 둘 다 괜찮을 것 같아요. 예, 이게 문제 삼지 않겠습니다. 네, 뭐 어차피 하면 되니까. 네. 예, 좋은 코멘트 감사합니다. 안 될 건 없을 것 같아요. Okay, any other questions or comments? Okay, see you next time.
교수님,
예,
혹시 그 건의사항 비슷하지만 뭐 한 말씀만 드려도 될까요?
예.
그 속도 표시하실 때 같이 V로 하면은 약간 혼란 있을 것 같습니다. 그래서 약간 벡터
그렇긴 한데
있으면-
제가 교과서도 찾아보니까 다 V로 쓰더라고요. 그래서 더 좋은 게 뭐가 있을지 잘 모르겠어요.
필기만 하실 때 쓰실 때 있지 않습니까?
예.
그때 위에 벡터만 표시해 주시면
알겠습니다. 그렇게
네,
하겠습니다.
감사합니다.
Okay, see you next time.